We have an action-packed evening today for you. I'm going to do a bit of overview of what we'll be doing this evening, and I'll be kicking off then with the first session myself. And then Siobhan will be coming in. We'll be doing every second talk more or less like last week. You can see a few changes here in our course web from last week. Something new here is our assignment. This assignment we'll be looking at a little bit later on. It's your first specification, and we'll be spending some time discussing it in the next hour or so. Last week's session you will see here. It's as we delivered it, except this time you will have the audio available. So you have audio and video for each of the talks that we gave last week, and of course the lab here as you might have concluded it last week. Okay, this week's session, I'll just dip into it briefly. It doesn't have any video yet because we're recording it. We're reviewing the Java programming language in some detail. Accelerated though, so we're covering substantial body of the language today with some more work next week. I'll be introducing the language in general, its background and purpose and some of its history. Siobhan will be then taking you on a tour of the basic syntax of the language. I'll be coming back in to talk about classes, one of the key building blocks. Siobhan will cover control statements. If we have time, we might skip this if we're running a little bit short of time. And I'll conclude with some general topics on object orientation in general and some of the language we'll have encountered as we proceed through the session today. We have our chat room open as usual. It's the chat room, as you can see on your right here. We also have the Gitter chat room still available. That's through this button here. I sent out a note earlier today saying we are opening yet another chat room, 3 chat rooms now. This other one is a private chat room. The one I'm showing you here is public. That is, anybody can join it, and it's also anybody can read it even if they're not part of the room itself. That's okay for just getting going, but we might like to keep our ongoing interactions a little more private. So you should have received an email about that, and as soon as you reply to the email, I'll invite you into the room. We won't use that room until tomorrow, and we'll still use the public one if people are out. I understand there's still some issues around Sun Life access to Gitter, so we will be keeping the Adobe Connect chat room going for the moment until those are resolved. And we'll keep it going permanently if they aren't. Okay, that's us to get started. As we did last week, we go through our talks. We pause for about 5 minutes between each talk. You can engage with us on the chat room there if you like. And then after 5 minutes, we'll resume and we keep that cadence going. Okay, I'm going to start now with the first session. We are going to review the Java programming language, and I'm going to give you some background and some early indications of the kind of structures that are used in the language, and we'll proceed with that for the morning, the afternoon. This is our general plan. Again, we're assuming you have experience in computing and programming in your background, maybe not Java. If you have considerable Java background, then a lot of this will be fairly routine to you. We'll go through it reasonably quickly, so hopefully it won't be too onerous. If you have another programming language, we're moving reasonably quickly through it, but hopefully you'll be able to tie in your own knowledge to the concepts we present here. If you've done Java at some time in the past, but not a lot since, then this is probably particularly useful as a refresher. We're not going to be covering all the topics I'm showing you here today. We're going to look at the overview, which I'm doing now. We're going to look at the basic syntax and arrays, which Siobhan will be doing. We'll be looking at classes, control statements, and then we'll probably stop at that point. Inheritance and collections is a topic for next week, and moving further into exceptions and streams, they'll appear intermittently in later weeks, perhaps not immediately. Okay, let's have a look at what we're doing then just for the next 20 minutes or so. History of the language, get a a view of where it fits, the basic syntax, basic structure of the language itself, including how we introduce variables and objects and naming conventions, and then arrays. Let's start with some of the history. Siobhan took me on a tour of the family trees last week. They are fairly extensive, and of course, Java is a key part of the modern evolution of programming languages. Java appearing in 1995. However, its origins go back quite a few years previously to 1991, and the original code name for Java was Oak. It came out of Sun Microsystems, and Sun, company gone now, was the shepherd of the language for its first 15 years at least. The language itself, interesting enough, was not intended for the use it became famous for in subsequent years, that is, as a server-side language for web and enterprise applications. Its initial focus was consumer electronics. I think the original application was set-top boxes, a prototype Sun product at the time. That's curious because it arrived back in consumer electronics many years later with the adoption of Java in the Android platform. But there had been quite a number of years when Java was maturing elsewhere in its history. It does have a footprint in embedded development. That's less so now, I think. In recent years, it's been superseded by other variants, either of Java, JavaScript, or more specialized embedded languages. However, you will find it on some older equipment. The language itself is designed to be portable. And this was an early differentiator of this language from other languages, particularly languages it was closely related to. Java itself could be considered a direct descendant of C++, and C++, of course, still going strong. Java shares a lot of its heritage from C++ constructs, but what it didn't take from C++ was portability, and the early decision to go for a virtual machine that was ported to different architectures was a key differentiator of the language. So the Java compiler always generates machine-independent class files, which are then compiled or interpreted, or sometimes both, down via JVM to run on specific platforms. Another key differentiator from C++ is memory management approach in Java, which adopts a garbage collected approach. This means that our objects, as they are created, are automatically destroyed. That is, there is a process running periodically in the background on our JVM, which is tracking, marking, and sweeping out the door any objects that are unused. This is probably the majority approach now of the languages we were reviewing last week. Certainly Groovy, Kotlin, to a certain extent Swift, all are garbage collected languages. Also Go is garbage collected from Microsoft. But C++ and C remain noticeably uncollected languages. And they're unlikely to be garbage collected in the foreseeable future. There is some performance implication with garbage collection, and the languages that require hard real-time requirements, which may include C and C++, often can't forego that requirement. We have a variety of versions, and depending on your organization, you may be on an older version. That's often for very sound reasons, to do with stability and compatibility. We're going to be focusing on most of the features as arrived in Java 7, but we will be revisiting in subsequent talks Java 8 and 9. So for today, we're sticking with version 7 more or less. The language itself was very stable for many years, a bit like JavaScript in a way, in that innovation was fairly slow, but has picked up in recent years, and from 7 to 9 has seen some significant new innovations. So structure of the language itself, we look at briefly. It's fairly conventional in terms of how we rules for identifying variables and types. We use letters, dollar signs are possible, underscores, and so on. There's a range of reserved words which we have to avoid, like in most languages, and our identifiers can't contain white spaces. They can be any length we like. These are typical examples of what we can and cannot use. Nothing surprising there, and it's mostly comparable to language you're already familiar with. The structure of a statement, particularly when we're invoking methods on objects, we have names for different parts of these lexical structure here. We sometimes talk about the message receiver, separator, a message, an argument, and a statement ending or a terminator. Here we're just invoking a method on an object, invoking a function on an object, you might think of it. And the notion of messages and message receivers and message context is it's a kind of language that appears in OO thinking generally, although perhaps not as widely used as it once was. Here's another fragment. Again, it will be largely familiar to you from other languages. Variable type comes first, then the variable names follow, and we may optionally provide some initialization of the variables themselves. So in this example here, this is the variable name, and this is the type preceding the name. We'll be seeing later on in some other languages slight variations on that. Particularly, we'll see some variations in the use of Kotlin, and we've already seen how Swift does it slightly differently. This here is an example of initializer. We're initializing a variable, via simple assignment statement. And of course, down here, we seem to be doing something else. We seem to be creating an object, and that object is now made available to us in this variable here. Semicolon is a valid empty expression, and if you're not careful, the empty expression can come to bite you occasionally. Here, a common error for people new to Java would be to use the semicolon in the wrong place. That is a terminator here, which means that this loop does execute, but doesn't print out the value I 3 times. It does nothing, and the printout statement occurs just once subsequently. If you're coming to this language from Python, this will look really weird because we have indentation here apparently expressing our intention. But indentation is entirely ignored by the Java compiler and system and has no impact on the execution. Okay, comments, as you would expect, they are inherited from C++, single line or multi-line comments. And there's a special form of commenting for documentation called java-doc-comments. And if you follow certain rules, which we're showing you here, then the Java-doc tool bundled with the environment can generate documentation in web form. So it is possible for us to have a comment something like this, and this is in our source code, remember? And if we invoke the appropriate processors, the Java-doc tool itself, then we're expecting this to produce a web page, which will give us something that's readable and browsable in this context. So this will produce this to a certain extent. We might be making use of that in our labs, although it's less important for the scale of the applications we're building. You'll probably be familiar with the structure as generated. If you've looked at any of the reference material we mentioned last week, you might have stumbled across pages that look a bit like this, which are the Java-doc output of some of the standard libraries. Java does support literals, of course, when we want to introduce constants of given values. Here we're declaring 2 strings. And of course, there's 2 slightly different forms. In the first one, we are declaring 2 strings, 1 and 2, and we're just introducing simple string literals directly into the program. This format is identical to the second one here. And this one, we're creating what looks like an object. We haven't looked at object creation yet, but effectively this notation here is a shorthand for this they're both identical. Okay, so that's just a brief overview of the structure of the language. I'm going to take a few minutes break here now. We can chat a little bit if you like, and then we'll come back in a few minutes to look at the basic structure of the language itself and to go through how arrays are implemented. So see you in just a few minutes.
Hi all and welcome back. I hope you can all hear me correctly. What we're going to do now is start moving on from what Eamon was looking at, and we're going to start looking at covering some of the Java basics primarily, and then what we'll do in this same lecture as well, we will move on and start talking about arrays. So you would have probably come across a lot of these constructs when you were doing your lab earlier on, but maybe some of them weren't clear while you were doing the lab. So this lecture will follow up on a lot of the constructs that you would have seen. So what we have is two of the main different types of variables that we're going to be using, two classifications of variables would probably be a better word to use, are primitive and reference. So what we're looking at here, this guy here, this is what we call a primitive. And in Java, there's 8 different primitives. This one here is called double. And what that is it's a decimal point. And we'll have a look briefly at those 8 different primitives. But you have another different type. In typical object-oriented languages, you have another type called a reference type. And this is what is here. This is a class that was defined called home policy. And what we're doing is we are building an object of this home policy. So home policy will reference where all of the information stored in that home policy object are in memory. So if we have a look at that, just a quick note there, recall that Java is a statically typed language, and that's why we have to put in types. This one's a primitive type, and that one is a reference type. So this is what we mean by reference type in pictures. So if we just look down here at the double premium, you can see that whatever value is assigned to premium, it's stored directly in the memory location that's associated with that variable. But if you look up here at the string greeting, what happens here is that there is a pointer, a memory location allocated to where the contents of that object is stored, in this case, hello world. So greeting doesn't contain hello world. What it does is it contains the memory location as to where the string is held. And that's what we mean by reference type. Greeting references where our string is stored in memory. And it's the same. This is only one string, is just one type of reference type. There are many more. We will write our own bespoke ones in this module, as well as using ones that come with Java. So we're interested in primitives. I mentioned primitives earlier to you. And you can see here that there's a thing called a byte, short, int, all of these lowercase guys at the end here. These are all different types of numbers. The first 4, byte, short, int, and long, are all whole numbers of varying sizes, byte being 1 byte size, and so on. They all increase in size. And then you've got your float and your double, which are your decimal points. A double is twice the size as a float. We also have 2 non-numeric types called a Boolean and a char. Boolean is same as any other language, which is true or false, and char is a Unicode value, which we'll have a quick look at Unicode as well today, and that is just stores 1 character. What we're interested in here is this is an inheritance hierarchy that we have on this slide here. And what this means is that everything, all of these guys, follow up. Say, pick short here. Short inherits from the number class, which in turn inherits from the object. Everything has object at its root, and we'll talk about inheritance next week. So it's just to draw attention to it there. So what we're interested in here is these guys are called wrapper types. And what these guys do is they convert our floats, our primitive types, into a reference type should we need it. We will explain to you why we need this at later stages when we move into the collections framework. But this is just an introduction to show that you can convert a primitive type into a reference type should you need it. And we will need it as we move through the module. And we'll draw attention to it when we do start using that. And these guys are called wrappers, and they're located in what we call a package. So a package is basically a collection of related classes that come with Java. We've multiple packages. We will bring you up to the API. We showed you the API briefly on the previous set of slides. That's what's generated from your Java doc, and it's our API is our application programming interface. And that's where we will go to find out what types of methods we can use with what types of reference types and so on. It's our reference for programming in this area. So the primitive types that we have here, these are the primitive types that we showed you on the previous slide here. So you've got your Boolean, your byte, and so on. And you can see the sizes allocated to each of these. And you can see the minimum values and maximum values. So you can see the ranges. 2 to the power of 32 divided by 2, taking into consideration the 0 value, will give you those values. So you don't need to know those values off by heart. Just know what 2 to the power of 32 is using your calculator. So Boolean has a value of true or false, and so on. So there's only 8 primitive types in Java, and that's the way it's been since the inception of the language. Your primitive types, we talked about the language, the classification of language, that when you choose a specific type for a variable, it will dictate the type of operators that you can use on that variable. So if we choose, so based on primitive operators, we know that if we choose int, byte, short, long, float, double, these are all our numeric types, we are permitted to do mathematical operations on them, remainders and so on, the modulo. And there's also like, increment first and so on. We look at all of these guys as we move through the course as well. And here's another classification of them. You're lesser than, you're greater than, and so on. All of these guys here. We can do these on our primitive numeric types. And also we can move on to our relational operators, our and our lazy and so on. So your operators are determined by the type of variable that you define, and these are our primitive operators. So do you remember we were saying it's a strongly typed language? So the type that we allocate at the beginning to a particular variable will dictate the operators that are available to it. So if we look at Boolean for an example, so Boolean we use it in control statements. It's got values of true and false. So when we start looking at our logical operators, there's only a few of these that we'll probably use on a day-to-day basis when we code. Not true. So the not, this is our invert. So invert the value and it will give us a false. So if you're not true, it's false. Not false, it's true. And then we're interested in the and the or. So both and, these are all back to your standard and gates and or gates that you would have done for any language that you would have coded before. So if you've got one true value and this on this side, both evaluate to true. So in order for a logical operator of and for the entire expression to be true, both have to evaluate to true. If either are false, the entire statement is false. So you can have a look at these guys and try these guys out in a CodePad, or try them out in Eclipse and just play around with these. So your char type. So Java is language independent, and what I mean by that is that there's underneath each char, what you have is a Unicode value relating to it. And you have Unicode, many Unicode values. Because it's a 16-bit value, you can have many Unicode values. And there are representations similar to what I've just highlighted here. There are representations for every character that can be possibly typed on a keyboard. I've included just a couple of them in here so you can see Unicode values. So the Latin capital for D is the Unicode value of 44. And there's many ones for the backwards or in Russian, for all different languages. So Java can handle multiple languages, and that's very handy from a localization perspective. There's escape sequence characters. A lot of C would have had these as well. And what it is when you include /n or /t within double quotes in a string, what it does is it says, the minute that Java sees the slash, it says, well, the next character that's coming after the slash is not part of the string, it's a command. So if I have a slash, Java recognizes that the N is a new line. The /t is a tab. So in fact, this, when you embed that into a string in Java, say you're printing something out to the console, Java recognizes these as being commands as opposed to being part of the string. And you'll find that you'll start using these for formatting output in console-based applications. So there's an example. Both of these are the exact same. So you've got system.out.println, hello. So println's print a line, system.out.println world. So there's two lines, or we can condense it into one full statement down here. And what we have in this is hello /n world. When the /n is embedded in the string, Java recognizes the second character, which is the N, as the command for new line. It's very handy for coding output to the console. So we've got numeric types. And there's just how our primitives fall into a numeric type hierarchy there. So we've got 4 integers, 2 floating points, and a Boolean. So when we start manipulating these guys, if we add 12 plus 24.56, it's a double. The result is a double. The lesser type is promoted to a greater type, and the operation is then performed. But in this situation here, a greater type cannot be promoted to a lesser type. And this is where Java starts giving out. So this is where it starts complaining about a loss of precision. So if I have a variable called I and it holds the value of 12 and it is declared as an integer, and I declare another value called D with a value of 23.4, If I try and assign D into I, there will be a loss of precision, and Java is very fussy about that and is not happy, and it won't let you do that. It won't compile. It will give you a type mismatch exception in your compile stage, and it will not do it for you. So this is where casting will come in. So we've got two types of casting. So in the previous statement that we were looking at, Java just refused to do it. It would not, what we call, implicitly cast the double as an int because it would have lost the decimal point. So Java will not implicitly cast that. And what it's concerned about is there's no information loss in implicit casting. So it won't implicitly cast if it's going to lose data. And you can see on this diagram here which directions it will implicitly cast. So a byte, if I can put a byte into a short, because a byte is smaller, has a less capacity than a short. In turn, an int can hold a short because it has less capacity. An int can go into a float because it's going to fit. There's a, it's just the decimal point is going to be 0.0. So you can see what we mean by implicitly casting is whether Java will automatically do it without the loss of data. But our situation beforehand, on the previous slide, it was a compile time error. It was complaining about a type mismatch. In this case, there is another type mismatch. Int I is assigned 34.5. Won't work. Java will not accept that. So what you have to do is you have to, in this case, explicitly cast and say, look, I know it's going to lose the decimal point. I'm happy with it. It's perfect for whatever application I'm building. Don't worry about it. Just put it into the I. I am aware. So explicitly casting is forcing a number that doesn't fit, in this case, doesn't fit into the variable and letting the compiler know, I know I'm going to lose data. It's fine. Just do it for me, please. So that's explicitly casting. So what we're looking at here is classes and interfaces. So AKA object types. So we've got two different reference types that we're going to look at in this lecture. So we will cover interfaces hugely in, I think it's next week we have that planned. So the reference types that we're interested in at the moment are classes. So if a variable is declared as a type of a class, an instance of a class can be assigned to that. And you saw that on Eamon's slides previously when he had a home policy and he assigned a variable, an object of home policy to it. We're going to go into detail into that. And you can also have an instance of any subclass of that class can be assigned to it. So subclass, this is what we're going to start talking about, inheritance. That is something that we will cover in 2 weeks' time. We're just flagging it with you again, that there is subclasses. We're interested at the moment in looking at just the classes themselves. So your interfaces. If a variable is declared as a type of interface, any instance of any class that implements that interface can be assigned to it. So what we're looking at is abstraction here. So the main things that we're trying to get across here in this lecture, we will delve deeper into interfaces. We will delve deeper into inheritance in the coming weeks. But we're just flagging that there are two different reference types. One of them is an abstract, is helping us build abstraction into our models, and another one is for inheritance. And we'll look at those guys as well. So uniquely identifying a reference type. We saw, when I showed you the slide on wrapper classes, I drew attention that it was stored in the java.lang package. So what we're looking at here is the wrapper classes would have been stored in a particular location. So it's the package where the class would have been stored. Generally, this translates into a directory structure in real life. So you'd have a Java directory. Within that directory, you would have a lang directory. And then all of your classes, which are Java files, would be all listed within it. So what we're doing is identifying exactly where our objects or our wrapper classes or anything that we're trying to use in our program, exactly where it is stored in that directory class. So the object operators. So we have multiple different object operators that we can use. And we will look at the reference types. We looked at a greeting, string greeting. The greeting variable is an object, it's a reference type, and its class is string. So we know that the object is an instance of string. We'll look at instantiation later and what we mean by that too. Not equal to, identical, and an assignment. We will cover these as well as we move through it. These are your object operators. So if we want to create objects in Java, what you use is a specific method. It's a special method called a constructor. And that's our constructor there. It is the exact same name as the class, and its job is to initialize the object to a starting state. So in this case, we've got an object called first policy, and it is a reference to where this guy has been built. So our first policy object is of type home policy. We have another here called second policy is of type home policy. And in this case, we have a constructor, but we're passing in data. So we have two constructors to build home policies, depending on what type of information we have at the time of building it. So if we look at the code behind that, there will be public class home policy. This will be stored in a home policy.java file. We have one constructor here. Constructors are always public. There is what we call no return type. So in here, there is no return type. We're going to look at that with you as well. And it will always be the exact same name as the class, which is up here. And the job of these constructors, there's one constructor, public, exact same name as the class, no return type. Another one, public, constructor with the exact same name as the class, and no return type. The difference between these guys is the parameter list. You can see here, there's no parameters. And you can see in this one, there is one parameter, double premium. So depending on whether I know the premium or not, I would choose to build my object using this. If I didn't know the premium, set the premium to a default value. If I did know the premium, I would use this one. I would invoke this constructor to build my object. And that's what we've done down here. The first policy, our premium is set to a default value of 100. And on our second policy, the premium is set to a value of 120. So what we're doing is we take in the premium through our constructor. This field is directly this guy here. And what we have is a this.premium. What we're saying is there's another premium, our field, and it's the one belonging to the class up here, this class up here. So it's this guy here. If I omitted this dot and just did premium is assigned premium, Java is incredibly lazy. And what Java will do is it will look for the variable declaration of this guy, and he will find it here. And if I didn't have this in front of this variable here, Java will say, oh, there's the variable. It will find it, and it will do a circular update on itself, and you will never update the field at the top. So these guys are what are called, at the top here, these guys are what are called your instance variables. So whenever I define a home policy class, each of them will get a premium variable. And it will be filled with either 1,000, or it'll be filled with whatever we set the premium to be. So the constructor's job is to build the object in memory and give the object a starting state. On our one here, we're just setting up premiums. And that's what it's going to look like. The first two guys here, you can see that we have, this is an object reference, this is our object. It is pointing to an area in memory that has a home policy of 1,100. It has a policy premium value of that. The second policy is an object reference to where our home policy object has been built in memory, and it has a premium value of 1,200. We have to be very careful with assignment statements when we're dealing with objects. Here's an example why. You can see in this up here, we have each of them is pointing to a distinct home policy object in memory. If I assign first policy is assigned second policy, what happens is I am not assigning the contents of these, what I am doing is I am assigning the reference, which is the arrow, the memory location. So first policy is now pointing to whatever second policy is pointing at. Okay, so we should be very careful with assignment statements. We'll show you how to jump into the object, retrieve data and set it up and so on, as opposed to using assignment statements and losing. Once you lose your reference, it's gone. Your object is lost in memory and the garbage collector will come along and pick it up from you. So identical objects. So these guys here, when we're dealing with primitives, primitives don't have a reference. Primitives, the value is stored directly in the memory, it's directly in the box, basically. So x is 3 and y is 3. If we assign x and y to be in both the same value, I can then say that x is equal. This is my equality operator. I can say that x is equal to y, and that is a true Boolean expression. But when we're dealing with equality with objects, what is happening here? All that we are doing is checking that they occupy the exact same memory space. So we're not checking the contents of the object, we're not checking the value of the premiums, we are actually just checking that they point to the same object. So we're checking references. And this is something that we need to be careful of, and we will show you how to get around that sort of stuff as well in as we progress through the module. So the reference type variables are identical if they refer to the exact same instance of the class, that is, their memory address is the same. So in this case, what we've done in this code is we have built one object called home policy, an object of home policy with a premium of 1,200. What we have done is build a second reference, an object type home policy, and its object name is second policy, and we have assigned it to whatever the first policy is pointing to. So there's only one object. We have a reference here pointing to whatever this guy was pointing to in the first place. So both of those are identical. We don't have two separate objects built. We've only one object, and they're both pointing to the exact same object. The reason why we don't have two objects is we have only called the one constructor method. So only one object has been built in memory. So equal objects. The previous slide, we looked at the double equal to sign for equality. And that double equals is absolutely legal, perfectly legal to use when you're dealing with primitives, because the data you're comparing is stored in the memory location directly associated with the variable. It is not legal to do it with it's unpredictable as opposed to legal. It's unpredictable to do it when you're dealing with objects. So the first policy, we are creating another object here. We know we're creating the object because we're calling the constructor, and we have two identical values going in both of these guys. So we know that we have two objects. We've called the constructor twice. There's one call. And there is another call. We have called the constructor twice. They both contain the same default initialized data. So when we do first policy dot equals, so what we're saying is first policy, invoke an equality check on it. And we are saying, does the first policy equal the contents of the second policy? We are comparing contents here in this. We are going beyond checking identity, which is the memory location, and we are jumping down into the object and we are comparing the contents of those two guys. So when we compare objects, reference types, we have two things that we need to be careful of. Are you comparing identity, or are you comparing the contents of the actual the contents of the object, as in the data that's stored in it? So we will look at this equals method in detail as we move through the module as well. We'll write our own ones and so on. Null. So null is known as the $1 billion mistake, and we will look at this. What it means is that I'm not pointing to anything. I have no reference. I'm not pointing to any objects. So it's a value that you can put into any reference type. So in this case, what we have done here is string. That's a class. 1. There's my object. 1 is pointing to wherever the data is going to be stored. The data that I'm storing is the literal ONE1. What I have done then is I have said on that object that is pointing to my data, my literal, I want to assign that null. So what I've done is I've overwritten the memory location of where my literal has been stored, and I have lost the reference to it. I have unassigned my object to its data. And in this case, then I'm just reassigning it with another value. So this object will be lying around in memory with nobody pointing to it, and the garbage collector will come along at periodic stages, and it will clean up objects that we have programmatically lost references to. So in this case here, we can use null for in another case as well. So what we have done here is we have said home policy policy. So on that line that I've just highlighted, what we've actually done is we have stated our intent that we will be calling a constructor more than likely at some stage to build an object, but we haven't physically built it. So we are waiting with a null pointer. The object has not been built. We will probably build it later on in our code, but at this stage of the execution of the program, policy holds the value of null. It is pointing to nothing. When I call my constructor, use the keyword new to call the constructor. When you call the constructor, you're physically building the object, and that policy variable here is going to point to that physically built object. So now policy has a memory reference to where your object is stored in memory. And I can do checks like if policy is not equal to null, then print it out. System.out.println, print out your policy. If I didn't do this check, this is why it's a $1 billion mistake. If I didn't do this check, and we'll be covering that as well later on, so this is kind of an overview of where we're taking the module. So if I didn't put this check in here and I tried policy.toString and I hadn't called that, if I had literally just had this and that was null and I tried policy.toString, my program will crash. What it'll do is it will go to the policy variable, policy will hold null, it will try and invoke the toString method over it. Because you're dealing with a null pointer, Java doesn't know what to do and it crashes your program with a null pointer exception. So what we have to do is programmatically control that we're not going to hit a null pointer exception. It will literally just crash your program and that's the end of the program. So because in this case, we have definitely built it. So this is just a to be sure check. So arrays, so that was just the kind of the Java basics. A lot of those items that we looked at there, it's a whistle stop fast tour. A lot of those items we will be coming back to in more detail as we progress through the next couple of weeks. Okay, so the arrays, what we're looking at is an array here and a collection. It's what we're dealing with an array. We've so far looked at primitive types, a variable in isolation on its own. We have looked at reference types. They are another variable in isolation on its own. Most times when you start doing anything meaningful with collections of data, you want to build some sort of a data structure that you can iterate over and manage. And that's what we are dealing with here with arrays. They're what's called fixed size collections containing the same type of element, either a primitive or an object, but each of them contains the exact same type of element. So it's fixed size. What we mean by that is you need to tell Java exactly what size the array is going to be. It can't grow, it can't shrink. The memory is allocated, it's done. And they're indexed. So each of these is an element of the array. We have 10 items in this array here. The array length is 10, but in order to access, for example, the element here, which is the third element, we would use index number 2. So what we have is we've zero-based indexing to access each of our elements. And we'll show you how to access them in a second. So if I try to access an element that didn't exist, we're back to a problem with another exception. And exceptions mean it's going to crash your program. So if I try and access an element in my array, my element is length 10. If I try and access an element, an 11th element, this is automatically bounds checked. And what will happen is it'll crash your program again with an array index out of bounds exception if you try to access it and you haven't programmatically handled for it. So declaring arrays. So you can see this here is a primitive. This here is a reference type. So I can have what are called a primitive array of either primitive values or of object types. The minute that we put the two square brackets here after a variable type, we are indicating that we are dealing with an array. So what I have here is I have a reference. This is an object. This is a reference to where my array will be built. Once again, if I have just done this level here and I haven't done any, called any any constructors and so on, this will be just a null pointer. So this guy is a string here. We are saying build an array of string and call it arrays of strings. I haven't given it any size yet. This is only me saying I am declaring my intention to build an array. It will be of type string. I will reference it with an array of strings variable, but I haven't built it yet. I will build it further on in my code. So these are interchangeable here. I can put the square brackets after the variable type, or I can put it after the variable name, and you can see that we have done that down here. So the second line here, the first line here is only declaring my intention that I will be building an array at some stage in my code. It will be called array of integers and it will hold a whole series of ints. And this is physically building it in memory. So this is us creating the object for the array of integers, allocating 5 spaces onto it. So we'll have an array of size 5. Once again, you'll see this keyword new. As soon as we want to build an object of some sort, we will use the keyword new. You saw it when we were using our constructors. We were calling our constructors. Constructors are invoked using the keyword new. And same here, build a new array of type integer with 5 spaces. We must specify the size when we're physically building it. There are different ways to specify the size, but you must specify it. And each of these guys, the initialization for this array of integers is the default value of int. So the default value of an int is 0. Default value of double, same again, 0. So it will be defaulted, the default value of each of those elements will be a 0. So there is another approach to building an arrays. We can initialize it using a string of using literals. So in this case, I can do, that's my intention to build an array of integers. And what I can do then is this physically builds it, gives it its object reference in memory. And by me passing in data, 1, 2, 3, 4, 5, which are valid ints, what it's doing is it's working out itself that it's an array of 5 and it's giving it default starting values to what we're used to, what we want here. However, we cannot do it, we cannot split it in 2 different lines. See here, this is a compile error. If we try and delay the building of our array using default values, maybe we read them in from somewhere, it's not really going to work. You have to, when you're creating your array, if you want to use a string of literals, it has to be done at the same time as you building your array. So this will give you a compile time error if you defer the initialization of it and the building of it to a later date. So if you're not using an initializer like we did using a string of literals like that, an array can be initialized by storing elements at a specific index. And this is an example here. We access each element using what we call the index. So the index is always the size of the array minus 1 is the maximum index. Indexing is always 0 based as well. So if I want to access the first element in my array that holds 5 elements, I use the index 0 and then I can assign it a value. Same here. This is the second element in my array. Give it a value of 2 and so on. So I can just, that was the previous slide showed assigning values to your array. This is accessing them for printing out values. So in this case, what we're doing here is we are saying array of integers, access the element stored at location 2. So location 2 will be the third element in our array. It's offset by 1. The index is offset by 1. So access my array of integers at location 2 and print it out to the console. And we end up with the value 3 here. We also have properties. We can access, this is a property, it's not a method call, and you'll see why it's not a method call is there are no parentheses straight after it. This is the property of an array. And what it is here is that array of integers. If I want to figure out how long my array is, what's the maximum size of my array, I can just have array of integers dot length, and it will return to me an integer indicating the exact size of my array. In this case, it will return 5 to me. We typically use this when you're using your for loops and using control statements. We typically use this in control statements rather than hard coding a value in a 5. You can also have multi-dimensional arrays. We won't cover these much in the course. It's just to follow through on the arrays here. We will start moving down the collections route, which is what's coming next week as well. But you can look at these guys here if you want in your own time. Multi-dimensional arrays, you can have any number of dimensions in an array. This one has 2 rows, 5 columns. You can have n-dimensional arrays. And this is just a diagram just to show you how the arrays, how you access them. And it's, you know, kind of all that stuff there. You can have a look at it and how they're laid out in memory. And initializing an array, multi-dimensional array, there's an example of it there as well. So we can still use our array initialization using a string of literals. That's no problem. And then accessing an element, you need your 2 indices to return the value at a location in the array. You need your row and your column. So what we've looked at so far then today is we have covered the basics and arrays, and we will be moving on after this. Eamon will be back to you in a few minutes and he will start doing all the classes. And if we have time, we will do the control statements, and we'll also talk to you about your assignments. I'm sure you're all dying to know about that. So I'll be back to you in a little bit. Okay, thank you.
Okay, we're back now to resume our review of Essential Java. We're looking here at our kind of roadmap. As I said, that our roadmap is going to span the first few weeks, certainly, and it'll be interrelated to other topics. So we're not just doing Java for the next 3 weeks, but we're doing the left-hand column today, which is overview, classes, and then control statements. So we've done our introduction. You can see roughly where Java came from. And the basic syntax of the language we've been looking at for the last few minutes, which Siobhan gives you an idea how familiar really it is with many common programming languages. And you spend quite a bit of time now looking in detail at the basics, how we declare variables, the kind of operators that are appropriate for variables of different types, the distinction between primitive and reference types, and then reference types in particular, how we create those, what it means to perform assignments on those, and then some very tricky areas around what if the reference variables are not initialized. We'll be returning to that in some detail later on. The mission now, though, for the next 20 minutes or so is to look at the classes in particular, and more specifically, how do we design and implement a class syntactically, and what are the primary features of a class once we have called it into existence. So classes, they go back a long time. First class introduced in a language called Simula in the late 60s. This was a language aimed at simulation, as the name suggests. And the classes were used to represent real-world entities under simulation in that context. The notion of a class as this type of entity was picked up very strongly by Smalltalk in the 70s and directly led to its inclusion in C++ and then onto Java. And of course, it's proliferated to many of the standard canonical languages these days. So we'll look at what a class is in Java, how it's defined, how it's associated with specific files and compiled entities, how they're packaged together, what a jar file is, and then also how we break down a class into fields, methods, and constructors. Classes have very specific fields and methods that are defined static, which we need to look at. And then we also need to look at some widely used methods that are present in all classes, which is something we will need to be grappling with as we proceed. So this is what a class looks like. It's straightforward enough, really. We have the keyword class. We have the name we're inventing, usually capitalized, and we have the visibility of the class. And for our purposes, we'll largely be running with public classes. This means they are visible outside the package in which they're defined and also outside the class file itself. We store classes in a file. We would name the file to match precisely the class name. So if we choose to call a class policy, then the name of the file must also be policy, and that includes the case of the name being consistent. If we step outside this, then we'd expect our IDE and Eclipse would be monitoring that and letting us know we're not quite adhering to rules. Classes are contained in packages, and the package must be declared usually at the very top of the file containing the class. And of course, the same package can contain multiple classes. So the same package statement here can appear on a dozen classes, and all those classes will be considered to be part of the same package itself. Naming packages is often done with reverse DNS to ensure some attempt at universality, but any name is viable. You don't have to use dots. And when we import a class, that is when we include it into another class, we must specifically identify what package the class comes from. In the first example here, we are declaring, creating an object of a specific type, and we're fully identifying the package name succeeded by the class name as we create the object. But in the second example, we're choosing something much more easy to work with. We're just using the class name because we will have imported the class explicitly early on in the same file. Again, this is an innovation over C++'s include mechanism. Its modules are supported directly in the language itself, and the syntax of the language is able to check that we're pulling in the packages correctly. We'll largely prefer the latter approach, except when we have the potential for ambiguity, in which case the former would be used. That's very rare. Back to our Javadoc output, you can see on the left here, we're able to distinguish between packages, which are visible in the given library we're looking at, and then individual classes within packages. So any class we're identifying here is in the context of the package selected in the packages list. Back to our diagram again. Our compiler is generally compiling one file at a time, and each file becomes one generated .class file. So we go from .java to .class via the compiler. Class file is binary, it's machine independent, and it's in a machine code designed to target the virtual machine on which Java runs, the JVM. We can see this in Eclipse if we reveal the navigator as well as the explorer view. On the left here we have a logical view, which is the one you would have seen from last week's labs. You can see the three classes we had and also the library we're using. On the right, we're looking at a physical view, which can be revealed if you do show view navigator. And here we can see there's not one source folder. There's a source folder, a lib folder, and a bin folder. And the bin folder is where the generated classes are generated by the compiler. So these classes one-to-one mapping to our package structure. In fact, the JVM only needs the class files to execute. It doesn't need the original source. Part of the machinery for achieving this is the JVM, the compiler rather, is looking for an environment variable called class path. These class paths then are used by both the compiler and the runtime to decide what class files can be loaded, where they're loaded from. So as class objects and classes are encountered at runtime, the machine code variants are loaded. This is highly dynamic, and it can be a complex issue, but generally we'd expect our tooling systems to manage this for us now. You may though have seen in our lab last week, you had to interfere in the build process by manually adding a library to your class path. And this was done via the GUI in our Eclipse environment. We had to download the Xstream component we were experimenting with, and it had to be added to the build path explicitly. Otherwise, we weren't able to gain access to the classes in the jar file at either compile time or runtime. Okay, some terminologies then that we will be familiar with as we proceed into the course: the class name and fields. Fields are central to the memory of the class, or to memory footprint. They are the state that objects that adhere to the class will be maintaining. Here is how they look as we define them in the source. The class policy has 3 fields: client, policy number, and premium, and the types are declared as if they were variables. And they are in fact variables. We call them instance variables. We have an additional qualifier here, the access modifier, which indicates how available the field is external to the class. Private would mean completely unavailable. Same rules apply for just conventional variables as Siobhan is exploring. If we don't initialize them, we expect them to be initialized to 0 for numerics or false for Boolean, or we can choose to initialize them ourselves directly as we would for variables inside a function. In this instance here, we're initializing a string to a given constant value. And here we're using another class, and this other class is of a different type to the class we're in. We're creating a client object inside a policy object using the new syntax Siobhan was discussing. Okay, so it's reasonably logical how it's laid out. The constructors also play a role in initialization, and they may be used to either augment or perhaps even replace the type of initialization I'm showing you here. And I'll look at constructors shortly. There are rules around these accessors. We've just discussed the private modifier, but there are, of course, two others. We have protected, and we also have public. When we discuss inheritance next week, we'll get a better handle on what protected means. Public, in effect, means the fields are completely exposed and visible. For the classes we'll be developing, we largely make the fields private and the members public. But that's just our convention for the moment. If we don't specify any visibility qualifier, then it's considered to be default. Default is not really a keyword in this context, and its visibility is slightly different from the other two. Largely means that classes and fields are accessible, members are accessible within a given package. Okay, we'll come back to this a little bit again shortly, but if we're trying to visualize the nature of an object and methods and their role, then it's useful to think in terms of methods delivering behavior and fields retaining state. So if we had a class object and it's a class construct representing a bicycle, for instance, then the bike in motion may have certain attributes like its current speed, RPMs of the machinery, what gear we're in. The behavior, though, which we control this state, we would visualize as methods, changing a gear, braking, or changing the cadence. In Java, all instances of class are the same methods. That is, the same methods run and are adhered to all objects. When we send a message to an object, we're executing that method. However, we're executing that method on whatever object we send the message to. Let's take a look at a more extended example. Again, you've seen this in Siobhan's exploration a bit earlier. Policy class may have fields, client, premium policy number, and then it has a range of methods. In this case, they're simple enough methods to retrieve or access the private fields. This is how it looks. Policy class as defined, and then we're specifying methods inside the class with their own access modifiers, return types, method name, and parameters. The constructor is a special method used in object creation only. It's named to match exactly the class name. It doesn't have a return type. It may have parameters. And it has a conventional body which can contain any initialization or algorithm we choose. In this example here, we're choosing to invoke other methods in the same class in the constructor. These constructors are triggered by the new statement, as you've seen. And here is a constructor that takes several parameters. We're passing a client object, a string, and a double. And we are storing those values directly in the object itself via the setters we've already defined. And at the end of the screen here, we're showing the creation of a policy object itself. New means it's created. It's created on the heap. It's garbage collected by default, as we discussed. And while we're creating the object, we're also creating a secondary object client, which is passed into the constructor. And we have two literals then we're initializing the object with. Okay, there's a more complete example of the same class showing you general structure and a particular indentation style. Now, moving on, still within the context of the classes we're exploring, we're looking at the specific qualifiers we can introduce that aren't visibility qualifiers, but are scoping qualifiers around the range and lifetime of specific fields and methods. And this is the static method, static qualifier. Here we've got a visualization here of perhaps a class bouncing ball and 3 objects, 1, 2, and 3, ball 1, 2, and 3, each one having their own position. If it's in a game and if we've got a physics engine, we may choose a specific gravity value for the entire game. And that gravity value may be expected to be enforced for all bouncing balls in the given simulation. We could have each ball possessing its own gravity value, but we choose instead to have one gravity which is shared by each of these objects. And in Java, this is made incarnate by the static keyword used when we're defining the field. So our incantation now is starting to look a little bit more lengthy. Public final static int. We're saying we've got a field called 1. It's an int. There is a shared version of this across all count objects. It will never be modified. That's what final means. And it's accessible externally. Public. Because it's accessible externally and because it's independent of any object, we can access it via the class name. You can see that in action here. We're using, because the capital C is used, we're using the class name dot field name. And this is quite valid because it's public and we're printing it out. We're doing exactly the same thing down here. We are accessing an info field, which is static, public, but we're accessing it via not the class, but an object of type count. And we have a choice of doing this one or the other, direct or indirect. Largely, we'd expect our style guide to give us advice on this, and the style guides will probably lean towards always using direct access, as it's more obvious what's occurring. Also possible to have static methods. In this instance, we have a static method that's retrieving a field. Field info is private in this instance. And we can access this method directly or indirectly, as we've been discussing. Indirectly means we're reaching from an instance of the object. Directly means because it's static, we can access it via the class name. And again, I'll point out the class name we're using here, count, is capitalized. So we're seeing clearly a different access mode. Static fields then move on to some other widely used methods in Java classes, and particularly where they reside and how we access them. Java implements a feature sometimes called a cosmic object. This is the notion that there is one class from which all classes are derived, even if you didn't explicitly make that decision in your class itself. Now, we haven't really discussed how inheritance works yet, and we'll be looking at that in a week or so. But there is this class object, which is at the root of all classes in the environment. This is a feature that differentiates Java from C++. C++, very similar syntactically to Java, but it does not have the concept of a global object. That notion actually comes from Smalltalk, which introduced the concept in the late 70s. So this class object, it's up there as the base class of all classes, implicitly defined. And this base class has a range of methods already defined for us and already implemented. Now, the number of methods is very small. This is the complete list, I think. So it's not like it's a substantial range of capabilities. And often we're interested in interfering or re-implementing a small number of these methods. In particular, we're interested in looking at the toString method and the equals method, which would be considered to be fairly important methods in how our class works. we also would probably need to keep an eye on the hash code method. The remaining methods, some of them are largely disused now and are like junk DNA in terms of how Java has evolved. Others are specifically associated with multi-threaded behavior, which we will not be covering. Here's the equals method. You'll notice in this code fragment, we've got an override directive, and we'll discuss that in next week's class. The equals method's job is to compare any object with another object and return true or false, are they equal or not. This implementation can be a little bit complicated, showing you a simplified version here. And in this version, we are looking at just seeing if the other object is a book. If it is a book, then we proceed through this rather complicated looking expression to turn the other object into a book and then reach into it to see, do the two strings match if a string is used for the ISBN. This is a little bit beyond where we're at for the moment in Java, so we'll be looking again at equals in a week or two. Hash code is another one. This is again a implementation already in the base class object, and in general, if we are putting our objects into collections and the collections are mapped in some way, that is, they are part of some key map collection, then we are very interested in the hash code and how it behaves, and we may need to implement hash code ourselves. This usually doesn't mean implementing our own hashing algorithm, but rather delegating to a hash code that might be part of one of our members. One interesting aspect of strings, which we've seen already but haven't really looked at in any detail, is that they are immutable. That is, when you create a string, you can't really change it after the fact. This may seem a little bit surprising, because very often we are doing modifications on strings as part of our business logic. Here's some examples of creating strings, but every time we do an operation here, we are generating often new strings from the old strings. So when I call, for instance, to uppercase here on hello, I'm not converting hello to uppercase. I'm generating a new string, which is a copy of the old one that is uppercase. If we do want to do surgery on a string, then we're looking at string buffer as opposed to string. And string buffer has some range of features to allow us to modify in place the characters of a string. You can see delete, replace, and so on down there. String manipulation is considered a little bit awkward in Java compared to other languages like Python or even JavaScript, and not one of its strong points. We've seen println occurring once or twice there in the earlier examples. Println is accessed via system.out, and this is part of the standard library. When we say system, we're reaching into an object that contains some standard features associated with the environment in which the process is running. When we say out, we're accessing a public static member of that object. So out is public static final stream, effectively. And finally, when we say println, we're just calling a method, and then we're passing parameters on that method when we pass the string in this instance. Okay, that's a quick tour through classes and how they're structured. In general, the labs really are where you'll get to grips with the structures and the concepts we're giving you guidance on here in considerably more detail, and they'll make it concrete. We're just looking at our clock here now, and we had planned to go through control statements, but I think it's probably the case that I will step through control statements, or rather flick through them very quickly, And we'll get on to object-oriented concepts because I certainly want to give Siobhan about 20 minutes to discuss your assignment. So I'll skip over control statements very quickly. I won't hand you back to Siobhan, and I'll spend a little bit longer time on object-oriented concepts, which is our final topic. Control statements, they're very similar to many other programming languages. So there is nothing really particularly new or groundbreaking in the way Java has modeled control statements. Various control statements you see here, if then else, switch, for, while, do while, they're all very familiar from the languages that Java derived from. So they're all almost identical to how these control statements work in C and in C++. And indeed, you'll find them very similar to the way JavaScript, also C#, also Go, and also Kotlin also behave. If statements, standard structure, some examples here. We can see we've got Boolean condition to be tested, and then the true or the false part. It doesn't matter how you use your braces in the if statements. Particularly, you may choose to have omit them for single statements or include them if the branches have multiple statements. In general, we would look towards style guides as to which would be preferable, and most style guides would suggest that this is the preferable style, even if you only have one statement on either part. Nested statements, need to be careful here. Generally, the old rule, an else belongs to the nearest elseless if. I think I remember from my college days. I think that still holds true 30 years later. Some more examples of nested statements. Switch statement is directly derived from C. It's a jump table effectively. It's a little bit old-fashioned now, and you'll see successor languages, particularly Groovy and Kotlin and Swift, have innovated and improved the structure of this quite significantly. Here's some more examples. The gotcha with the switch statement is the break is needed. And if you leave out the break, then you get a fall through where possibly all branches can be invoked. Again, that's not Java's fault, that's C, and that's almost goes back to original assembly language that C tried to supplant it. Okay, the loop statements are for, again, this is almost universal now in most programming languages. You can see the basic structure here, you should be used to it. And the strange notation here is how we would introduce an infinite loop in an expression. And the while loop, again, while loops are quite straightforward and identical to as they would be in C and C++. Do while loop ensures one iteration at least before determining how many iterations should take place. Okay, that's a very quick whistle stop of control statements. I don't plan to do any more on that really, and it's something you can look at yourself in your own time if you want a refresher. Okay, I'll conclude before I hand back to Siobhan and discussion on the assignment with just a brief review of some of the terms we've already seen today. And these are the object-oriented concepts we've been encountering, particularly this diagram. We talked about methods and behaviors. I think, Dan, you liked that example. We think of object state being the memory of an object and being retained by the fields, and these fields are sometimes called instance variables. We then regard the methods as an expression of the behavior of the object, and these methods can be invoked or triggered on the object by sending a message to it. We aim to have objects that are loosely coupled. That is, the bindings between objects are fairly clear and obey specific rules around the relationship between the classes and the packages in which the classes are embedded. It's very easy for us to evolve a very complex set of relationships that would be difficult and challenging to maintain. And we'll be looking at how that can occur and some principles for avoiding that a little bit later on. You will see in the OO world diagrams like this. This is a sequence diagram showing you what might be happening in a given scenario if several objects were interacting. Broker, policy, person, object interacting in this instance. And we're seeing here a swim lane or timeline of an object. And in this context, we're looking at how methods are invoked. And then if methods are interacting with other objects, how we can model that visually. These diagrams now are often automatically generated as opposed to hand-drawn, and we might do a little bit of experiments on that later on, of course. In those diagrams, we talk about a message sender and a receiver. The receiver is the object that is being invoked using the message that the sender is choosing to dispatch. Again, we've seen examples of this in the code fragments you've looked at to date. This is how we might visualize what's happening over a given time sequence. Now, one last few phrases that we'll be encountering again. The notion of considering the public methods of a class to be its protocol, or rather its public protocol. That is, if we have access to an object and we want to interact with it and use it, we can only use the methods that are made visible to us. If there are private methods or protected methods, they are not available and we can't invoke them. So Java, being strongly typed, adheres fairly strictly to this rule. It means that the compiler is able to police exactly what you're doing with an object and prohibit you from going beyond the scope or protocol of a given object. In fact, that very much characterizes the static, strongly typed nature of Java. If you're working in JavaScript, of course, those bonds are completely unleashed. Fields, as we mentioned, are often private, sometimes known as instance variables. They're the state of the object. They are the object's memory, and they retain in the fields specific values associated with a given point in time in the execution. Encapsulation is a principle. It's often called implementation or data hiding. Principle whereby our classes retain privately access to the fields, which means they're only exposed via public accessors. Common pattern in Java, perhaps a bit less emphasized in other languages. And then this coupling and cohesion notion. This requires careful consideration as we evolve our classes into form a system to perform some function. If the classes are all coupled across packages and extensively between each other, then our design is said to be very high in coupling and perhaps also low in cohesion. If we can reduce the number of dependencies and where we have dependencies, retain them within the context of a module, then we talk about higher cohesion and lower coupling. And there's strong guidance to show us that the overall stability, lifetime, and maintenance burden of systems is considerably alleviated by going for high cohesion and low coupling. These principles predate object-oriented thinking, and they've been taken into considerable detail and comprehensiveness since object-oriented arrived. Another notion of classes, we could consider them to be factories for creating objects. We could regard them as a template for creating objects of the same size, same type. Depending on the language you're dealing with, then these terms may be in use or may be used in associated literature. If we're talking about instances, then every instance is the same. It's a boilerplate generated by the class's constructor. I have a class called person and I create two person objects. Then I'm looking at those two objects identically structured, but of course their fields contain different values. We may also say that those two objects, though, have the same or support the same protocol. That is, we can interact or trigger their behavior using exactly the same signatures. Now, inheritance is something we've mentioned once or twice, the context of this cosmic global object class we all inherit from. But of course, there's specific inheritance, which we need to discover in a bit more detail in the next session. The policy class we've been exploring here may be a base class for customized or what we call specialized policy classes, home, auto, and life. And we would use the terms generalization and specialization in this context. Home policy is generalized by the policy. The life policy is a specialization of the policy class. Now, inheritance is a somewhat controversial topic, and we will be devoting some time to it in the future. It could be used for reuse. It could be used because it represents some real-world concept. I hope you like that one, Dan. Bicycle, mountain bike, and road bike, and tandem are bicycles, so we can model them directly in our class constructs. However, inheritance is a subtle topic, and there's more than one type of inheritance. And in fact, we will be drawing your attention to good inheritance practice and what is now considered to be bad practice. And we'll discuss those in some detail in a future class. Polymorphism is a central building block to object-oriented thinking. And it relies on a variety of inheritance. It could either be good or bad. We'd hope it would be good when we make use of it. Centers around the idea that when we're sending a message to an object, that is, when we're invoking a method in an object, we may not know exactly which method is to be triggered, because there may be more than one. If we're using inheritance, and if we define a dog and a cat as derived from animal, we have three methods here called talk. And when we invoke talk on an object, we may not be quite sure as we invoke talk which one we're getting. This is through the magic of overriding and inheritance, and it's a central feature of the language and how it works. It draws from the dynamic binding capability of the language. Dynamic binding being, again, a key feature of object-oriented languages in general. And if I have access to an object reference animal and I invoke talk, then I am calling a method, but I'm not quite certain which method is invoked. That'll depend on how I am dynamically bound at that point. Again, we'll see that in action in the labs, I think, rather than abstractly here. Okay, take a short break now, and Siobhan is going to introduce you to the assignment then. Don't worry about the brevity of our introduction. Your assignment is several weeks away, and we can come back and revisit it in subsequent weeks. The assignment specification, as I mentioned at the start, is not in our current topic, but is up here in our assignments area. And just before Siobhan gets into it, and before we have our little break, our labs are very much designed around preparing you for this assignment. So our next few weeks' labs are a bit different from last week. Last week was just experiment, probing some features. The next few weeks will be building up the baseline for your assignment, which you'll be invited to complete. Okay, I'll take a little break now, and then we'll be back. Siobhan will be back with you shortly. I won't see you again until next week. Okay, see you in a few minutes.
Hello all, welcome back. So I'm just going to go through the assignment with you. I'm sure you may have looked at it during the break or at something like that. So what I'm going to do is briefly go through this with you, and we'll finish up at 7. So what the plan is that I'll go through this with you. Some of the stuff that we're going to discuss in this you won't have covered yet. So don't panic basically. Your lab this week will start you down the road of the assignment, as Eamon was saying, and a lot of the labs that are coming up will build a starting point for this assignment. So some of the stuff that we do cover in this assignment you haven't covered yet, but you will over the next couple of weeks. And Eamon will revisit this assignment brief next week with you after you've done the assignment, or the lab this week, and hopefully it'll make more sense to you as well. So what we're looking at for the assignment structure for this module is, as we said earlier, it's 100% CA. So the first assignment, it's going to be worth 40%. And what we're planning on doing is taking it up on Sunday, the 5th of November, 2017. And what we have is a hard deadline on that. So we'd appreciate submissions on time if that's okay. And obviously life gets in the way. So if there are any major issues, of course, contact Eamon and myself. The presentation, we're not going to get you to do a presentation on the first assignment. You may be asked to do a code walkthrough. Chances are not. But what we're looking at with assignment 2, which will be presented to you week 7, in around week 7, maybe week 8, depending on how we're progressing with the content. We will be taking that up on Wednesday, the 3rd of January. And we will get you to pre-record a session, a 5-minute presentation or video. We'll give you a template for the PowerPoint, and we will get you to do some level of a code walkthrough on that assignment. So the first assignment, you probably won't be asked to do any code walkthrough, and the second assignment you will. So what we're looking at doing is getting you to build a pacemaker app. So what we're interested in is a command line interface application, so a console-based app. And in your labs this week, you will be downloading a component that you can use to help you develop console-based apps that will do a lot of the support for you in managing the console. So you'll get to grips with the console during the labs this week, and then you can progress this lab on, or this assignment on further. So what we want you to do is design and implement a simple activity tracker. Now we will be giving you screenshots that I'll show you in a minute. So there will be a lot of support in what it is you have to design. So the application is to manage activities for multiple users, enabling activities to be created, read, updated, and deleted. So what we're interested in this assignment is that in Java, you'll be writing a CRUD application using command line interface console or component. So what we want as well is to see that the application is persisting data beyond the life of the application, so that the user and activity data is stored to a file. 2 file formats, support 2 different file formats in the application. So XML, we'll be covering that with you as well, with Xstream and unloading into XML files. And there's also another format, JSON, and so on. 2 minimum formats. You can choose to unload into any format you fancy. YAML, so on. Labs will proceed to build approximately 50%. So as Eamon was saying, that we will actually, your labs for the next couple of weeks will start you on the path of building this. And you'll see on the screenshots that we're going to show you in a second that some of the commands will already have been implemented, and your job is to implement the remaining commands. So please submit partial solutions as well. Kind of something is nearly working but not fully working, that's fine. Submit it to us and we'll be able to ascertain how close you are to solving it and getting it working. So this is the command set that we're going to be asking you to do. Now, all of this console here, the prompt and so on, and all of this, it will be provided by the component that we are asking you to download. It will provide support for listing all your commands and so on. And we will step you through that over the next couple of weeks, getting you used to using this cliche component. So these are the list of commands that we would like you to implement. As I said earlier, some of these commands are already implemented in the labs. By the time you finish the labs, they will be done for you, and you just need to build extra ones. So one of them is the create user, and you can see it's command line that you literally type in CU for the create to invoke the create user functionality. And if you see down here, the create user has first name, last name, email, and password. So it's a prompt in how you are to enter the details on the command line. So when you create user, what it's doing is it's outputting it here in a lovely format. This is using what we call an ASCII table, and we'll discuss that with you as well over the next couple of weeks. As I said to you, don't panic yet. If you're not sure what ASCII tables are, cliche, a lot of the labs will support you through this. So also there's an add an activity command as well, and as you can see here down on this screenshot here, it shows you what your the parameters are for this command, and list your activity for the user 1 and so on. So you can see that what it's doing is you're adding locations to a particular activity for a particular user and so on. You're listing all of the users, and it's formatting it in a nice tabular format. And then you're listing list users for a particular email. So you're pulling up a user based on their email account and just listing out their details. Listing a user based on their ID. So you're deleting a user by passing in their ID. And when you list the users again, the ID has got the user has been deleted. So this is what we mean by the CRUD app, that you're implementing create user, create, read, update, and delete. And then what we have is a sort. This is one of the most advanced parts of the assignment, is building in a sort functionality. So listing activities and sorting by type, sorting by distance, and so on. So that is a challenge. The sorting part. Change file format. As I said earlier, that there is JSON or XML. Basically, what we want you to do is persist the information that is in the collections out to either JSON or to XML, different formats, and allow the user to choose by issuing the CFF, change file format, and one parameter, the file type, and that they can then load a specific file of a specific type and store to it. And there's changing file format back to XML and storing all the information to XML, and loading and storing all the information. So what will happen when you're finished? I think it's the first 4 labs that first 4 weeks of labs will support you with this. And you'll see that some of these commands will be implemented in the labs, and there is a series of commands that haven't been implemented that you need to do. And we've highlighted those in red, and they're the ones that you need to implement beyond the solution that we've given for the labs. We have a rubric here, and we can cover this again next week with you, because once you've done the first lab using cliche, this should make a bit more sense to you as to what we're asking. So what we do is generally we give a rubric for each of the assignments we give, and what it does is it gives you an outline as to what to expect, where you're going to position your submission. And you can see clearly here that the core features are worth 30%, and you can see the commands that we've listed that would baseline. Baseline is basically you're securing a pass roughly there, and everything has to work perfectly in that baseline for you to secure a pass. And then you start progressing up. So if you want to, if you're aiming for a good grade, you need to include everything in the good and in the baseline and so on. So these are all of your core features. And the outstanding level, this is like if you want to go basically bananas with the assignment, I get a really good grade, you can hit this level here. So the core features are listed there, and they were on the screenshots in front that I just showed you. Presentation. We were using a tabular presentation on those screenshots. We used a component called ASCII table to produce those. So that would be in the excellent level. They're black and white. There's nothing overly special about them. So there are lots of other components out there that you can really enhance the command line interface experience for the user. And that's, this would be outstanding if you go and research and figure out what components am I going to do. So plain presentation is just simply throw it out into the screen, no formatting. Pretty, you've put some thought into it, but you're not using a component. Tabular, you're using a component like ASCII tables. And enhance, you've gone way beyond ASCII tables and you've started to look at other different components for enhancing the layout. Testing, we will start testing, I think it's in week 4 with you. So we will talk about what we mean by basic API tests. This is all the JUnit stuff. We're going to do automated testing with you, and we will discuss what those mean. User interface tests, you will see the user interface tests are going to be, you're going to write test scripts and so on. There's part of one of the labs as well. The lab will step you through how to write a test script. You just need to take that further and add it into your assignment. We'll talk about what we mean by average accurate coverage reports as well. So we're talking about the JUnit automation of testing, and that you have actually exhausted all different paths of execution in your program, and that, you know, all possible reasonable ones. And you'll use tools like Jacoco. We'll go through this with you as well. That we'll use tools like Jacoco that will produce a report of how have you tested all different avenues, as in all different parts of an if statement, the branching, the switching, and so on. Have you tested all different avenues that can be taken in your program? So we will talk to you about what that is when we get onto the testing area. Build systems. We haven't done build systems yet with you. We'll be bringing those in, I think it's week 5, and we'll be using Maven, which is one of our build system tools. We'll be using that to build our application. So we won't be clicking the green button to run stuff. We'll be using a command line interface to Maven to execute, to test, to automate the pulling down of components. We're not going to be messing around with going up to GitHub and looking for a particular file. What we want is to automate all of that so that we will send Maven off for us to go and find the components, pull them down, and so on. We'll just tell it what version we're looking for of a particular component. And that is, Maven is one of our build systems, and Gradle is another build system. We'll cover Maven with you, and Gradle we will leave as something that you can explore yourselves. It's once you can do Maven, you can do Gradle, you can do any of the build systems. Once you have a handle on one of them, the rest of them will all be fairly easy enough to follow. So Eamon will go through this more with you once we've covered, when you finish the lab, he'll go through more with you, and it should start falling into place as to what's required, particularly in the core features area. So submitting the assignment, so we have the hard deadline there. So we'll get you to submit it through Moodle. We'll introduce you to Moodle at some stage next week, and we'll show you what we mean by assignment drop boxes and where they are and how to access it and so on. So one thing that we're asking you to include with your submission as well is a README file that will give, and we've underlined very, 1 page maximum. So don't put any effort into this. This is just literally Notepad. Notepad is fine, Notepad++, throw something in, a very brief summary of your submission. What we mean by a brief summary of the submission is what persistence approaches have you taken, what presentation approach have you taken, what was the testing approach, and what was your build system approach. And identify components, plugins, and so on used in your assignment. So it's literally to basically go back over this and have a look at what have I done in my assignment. And just a really brief README on that. So that's it for today. Thank you very much for listening. We'll be, as usual, we'll be on the Gitter chat room, and we'll start up in here as well on Adobe Connect tomorrow at the usual time, Irish time, 3 to 5. So whatever time that's in America, I think it's 10 to 12. I can't, yeah, it's on the slides anyway. And we'll talk to you then. Thank you very much, and we can answer any questions then. Enjoy. Take care. Bye-bye.